All right, I think everyone is settled down, and I can start. Right, so my name is Sue. I'm going to talk about how you can scale up and out, and what does that mean? It's up and out, and using Numba and Dask, and how you can program a GPU cluster with these tools. So a bit more about me. I'm a lead developer of Numba at Continuum Analytics. I've been working on Python compilers and GPU computing for more than 4 years now, and that's my GitHub account. So what I'm going to talk about first is let's define what is scaling and what does it mean to scale, and when you scale up, how do you do it, and is there an easy way, and probably that's Numba, and scaling out with Dask. Finally, I'm going to show a quick example of doing that. So understanding scaling. The reason you want to scale is to get more performance, but what does performance really mean? How do you measure performance? The usual 3 metric you may think about is latency, get faster CPU, you want higher throughput, you may use a GPU, processing more data items per second. Capacity is like RAM, your disk. Can you fit your data on your disk? Can you load your gigantic matrix into RAM? If you can't even do anything. But all these are really just hardware performance. Once you bought your hardware, you can't change them. But for software performance, you need to think about is utilization. When you get more utilization, you can really use those latency, use those throughput to your advantage. But when you do that, traditionally, you will be increasing the complexity of your code, and you want to avoid it. So when you scale up, just getting better CPU, getting better RAM, more RAM disk, that's the simple way. Decrease latency, easily increase throughput, same OS. You don't have to change your programming model. You just get performance for free. Not free, you still have to buy your hardware. But when you go to GPU, now you have to think differently. You probably have a higher latency when you do this computation. Things have to ship over the PCI Express to the GPU and back. There's higher latency. But you may get more throughput, so that may be a good trade-off. But complexity definitely increases. You have to change your programming model. GPU doesn't execute like your CPU. You have to rethink the problem. Maybe use new languages, change your code. And it gets even worse if you go to multi-GPU. Like, how do you even do that? That's a big problem. Scaling out is easy for the IT department. They just buy more hardware for you. But the programmer, that is hard. You may have more RAM, but they are like on 10 machines. You still cannot load your big matrix on one machine. You have to think about how do you segment your program. So again, it's higher complexity. And probably in the best of both worlds, in the 2 dimensions of scaling up and out, the best of both worlds is maybe getting a GPU cluster. Every machine has multiple GPU, and now you have many of those. But how do you program it now? Scaling up, how do you improve utilization when you scale up? Do you write Python, change your Python code to Python, and maybe that's not enough. You go to C, C++, and if you want GPU, do you program in CUDA C or OpenCL? So this changing language is a hard problem. Scaling out, do you go to traditional MPI? That's a easier way, comparing to adding gigantic infrastructure like the Java ecosystem, figure out how you put your data on Hadoop and Spark. So there's a way, and I'm going to show you how you can do all these without changing language and without installing large infrastructures. So with Numba, it would help you scale up single node utilization and not increase any complexity of your code. So what is Numba? Actually, anyone are using Numba already? Can you make sense? So, okay, so there are still people who are not using Numba. So what is Numba? It's a type specialized JIT compiler for Python. What it does is it takes your Python code and translates it into machine code. Now, that is how it helps you utilize. It's no longer running a Python interpreter loop. You are getting machine code just like you would write C code. The code generation is all done with LVM for CPU, and NVIDIA has their forecore NVVM. That's for their CUDA GPUs. But let's not get into details of those. So let's see how it is used. So just on CPU, this is Numba for CPU code. If you look at the code, ignore the top tech decorator for now. The JIT, ignore that. It is plain, pure Python code. It's using NumPy. What is this NaN compat function? What it's doing is, given an array, I'm going to filter out all the values that is NaN and compat it, skip all those values. But once you add this decorator, Numba kicks in. This is a decorator from Numba. It would analyze your code, compile it into the machine assembly equivalent for this function. So the only complexity is that line you have to add. There's really nothing for you. And at the end, you get a 2.x speed up, to 2.7x speed up for your code. And here is, once you add, even though it's machine code, you can still use their array allocation, the NumPy empty-like. There is, you can iterate over your ND array. You are still using NumPy functions, but you are getting bare metal performance here. So let's go to GPU. This is a CUDA kernel written in Numba. The computation, the execution model is a bit different, but at least you're still in the comfort of Python syntax. This is like a map function. You can think of this as a map function. This function would be mapped on the entire array, and it's doing the same thing as before, the NaN compat, basically. The only thing that you add is this new CUDA JIT decorator, and now you can, within this function, you have access to hardware intrinsic, the GPU hardware specific, the block, the threads ID. Those aren't normal in your CPU Python. And you can easily use it with your NumPy arrays. Numba will automatically copy any NumPy arrays from your CPU over to the GPU and back. You don't have to care about it if you want. If you want more performance, you can control it, but I'm not going to show that much detail for now. But those maybe a little bit more work. Here's the simplest way to do it. Using ufunc, universal function. There's a concept from NumPy. Is given a scalar function, you map that function over the entire array, element-wise fashion. So what I show here on the bottom left is 3 ufunc. The code in these ufuncs are exactly the same. Sine of x plus cosine of y. The only difference is the targets in the decorator. So vectorize target CPU. That's for sequential CPU code. Just change the string to parallel, you have multi-core performance. This now emitting scheduling for multiple threads. Switch that to CUDA, suddenly you are running on GPU. Now, there's no complexity change. And on the right columns is just some time its benchmark. In the chart, you can see the parallel in our 4-core CPU that I was running on, easily 4x speed up on the CPU throughput over the sequential one. The GPU easily get a 6x. Remember, like people say, the NVIDIA benchmark always exclude the device transfer. This includes all of those. This is actually what you will get. Now, on scaling out, so how do you do? There's also a simple way to help you utilize the multi-node machines without complexity. So what is Dask? Has anyone heard the yesterday Dask talk? That's great. I don't have to do so much introduction. So it's a flexible parallel computing system that it has many high-level APIs, provides things like arrays. Back is like Spark RDD. Data frame is like Pandas API. Those helps you build a task graph, which the scheduler in Dask can schedule it on multiple threads or multiple process, and there's even a distributed scheduler so that you can run on remote nodes. This means this is pure Python and helps you easily scale from laptop to clusters. And with Numba, you can do GPU clusters. But the API that I'm going to talk about, I think they also talked about that yesterday, is the delayed API. This is a very easy way for you to build custom task graph. And here is a simple image registration example. So on the left box is all, if you ignore the decorator, it's just Python code. Once you add the delayed operator on it, the decorator on it, they becomes task node constructors. When you call them, they don't execute the code in there. Not at that point. It just creates a node in the graph. When you schedule it, it will execute the contained code. On the right is the composition, like how you turning all those nodes, how you glue them together. So here's the correspondence of every node constructor used in the composer. Notice how on the right-hand side, it looks like this Python function calls. This function returns a delayed object. It's like a proxy of this task node. And you are not doing computation at that point. You're just building a graph. But it feels like the original thing. You can do attribute access, and here you can see we are doing get item on this deferred node. Everything helps build up this graph. So starting with this composition function, once you call it, it builds a graph. And it's kind of beautiful to look at. But the really cool thing that I found is, if you look in this part of this graph, it actually resembles the paper. There's a flowchart in the paper that I kind of, for this algorithm, that's on the furthest right. That's the paper. That's how the algorithm should look like. And you can see how it corresponds. So it helps you understand your code. So help you cope with, like now, this complexity of delayed, but you can easily see. You can still see your algorithm in action. And this is just a sample of how the algorithm would look like, the outputs for this image registration. And then the cool thing that Dask do is optimization on your graph. It's a really good way. Maybe I should show what it does first. So the arrow, the endpoint of this arrow it has this gray image function calls, or this task node creators. There are 3 of them, but in the graph, there's only 2. What happened is that Dask know that this is a pure operation, and 2 of those is gray image on the subject, applying gray image function on the subject image. This has already been done previously, so it just fuses them. You would say, okay, this symbol function, this is like a beginner programmer mistake. You can easily fix that. But what if your program is big and these are actually separated into 2 functions? That now is really helpful. You have the task graph optimizing for you. And you don't have to do this tiny micro optimization yourself. So what does it mean to scale out with Dask distributed? In the local execution, this is what I've shown right now. So this algorithm works by given 2 images. This is a JPEG image, just compressed image. Feed it to my Dask graph builder, ingrad function. D is now a graph, and I call d.compute. That's the local case. That can be run on multiple threads or in multiprocess. Going remote, going distributed, you just add 2 lines. You use these 2 width contests. The Dask distributed executor, you create one that kind of establish a connection to the scheduler. And then you kind of tell the Dask to set an option that do all the computation on my executor, on my scheduler that is specified. Then the compute line is the same, d.compute. So you can just change the top level code. Not going deep, you don't have to go deep into your algorithm to change that. And to launch scheduler, it's just 2 commands. This command, Dask scheduler, and there's also the launch workers with Dask workers, and it would spawn a process using all the core, 1 threads per core on your machine. What about MultiGPU? I found that Dask is now my favorite way to utilize the multi-GPU machines. Before, I have to do crazy custom GPU scheduling code right deep inside my application. It's too complicated. But now with Dask distributed, even on this single machine, you can use that on a single machine. It doesn't have to be remote. I launch a worker per GPU if I have multiple GPU. There's an environment variable. It's not Numba Dask specific. It's CUDA specific. It's something that CUDA driver understands. Said that CUDA visible devices equals then a GPU ID. So 0 is, for my case, 0 is a K20C. Number 2 is a K20C. The two GPUs. Two workers, same machine, and now you use Dask to schedule on them. That moves the multi-GPU scheduling out of your program. So the complexity is no longer in your program. It works the same as if you have one GPU. So it's just when you deploy. The other thing, this is a quick tips, is you want to use this NVIDIA CUDA MPS service, the MultiProcess service. It's a way, maybe I should read why, is if without this service, you can only use one CUDA program per GPU at any given time. Otherwise, it's like time sharing. But for my K20C Tesla big GPUs, I'm not fully utilizing it. I want to do better utilization. This is another NVIDIA tools to help you. It's not from us. Launch it, and then all multiple CUDA process can share the same GPU and compute concurrently. So get better utilization, things can overlap. Right. Now let's combine the two, Numba and Dask, scaling up and out. So my full application that I use to test this is a kind of automatic image stitching, not image processing expert here, so things that I'm doing here may be weird. So I have a bunch of image fragments. I need to stitch them back together. It's like a solving puzzle game with the computer. And start with, the algorithm works like this. So it is to group similar images using scikit-learn clustering. That's easy, and the SGL is very quick. The expensive part that needs GPU in the cluster is the image registration and the stitching. It uses a lot of RAM. I'm kind of decompressing them and then doing all the work. So part of it that I have is already compiled with Numba, there's a cross-power spectrum phase correlation thing, this Numba compiled. And I'm leveraging the FFT, there's a cuFFT package from NVIDIA. I'm using that so that I'm doing FFT on the GPU. And FFT is kind of known for NVIDIA card. It's easily 2x faster than MKL, I've seen that. And the whole thing is iterative. That means the task graph doesn't have to be one big chunk all the way to the end. You can keep just sending new task graph, keep repeating the process. We have a bit time. Let me do that. So I'm going to do a quick demo. Hopefully, I still have the connection to my company computer. Yes. I'm launching scheduler. I'm launching two workers. And so this is the machine that I was talking about. It's 3 GPUs. I'm just using the 2K20. And the GPU ID here is actually just different. The really cool thing about Dask distributed is you can look at the status page. So this is the status of the scheduler. I'm going to launch my application now. It will take a few seconds loading all the images. I have like about 30 images. Send it over. Right. It's now running, and it's doing the GPU. And the only way you can tell is from here. This is the introspection from NVIDIA to, you can see that the GPU RAM keep changing in this terminal. And this gap is the scikit-learn clustering part, and each iteration, the gap in there. But you can look at how this task is running. You can look at what is spending most of the time on, because otherwise I find it's hard to do multi-GPU profiling. This gives you a good way to give a sense of what is spending the time. So, right, so let's let it run. So application performance, for my toy example, So starting on the left is just one machine, but the host is this laptop here, the OS X. The worker is a Linux. It's 4 process, 2 GPUs. I always have 4 process per node and 2 process per GPU. So once you go to 8, you easily get, it's almost a linear speed up here to Linux. The last one is just for me to have fun. I'm adding Windows box just to show you we can do like heterogeneous OS. Then we are compiling all the code on the node, so it's fine. We are calling the right system calls all the time. And it's also a mix of GPUs, like 750 Ti, K20C, K40. That doesn't matter. This is a JIT. We specialize on the hardware. We know what you're running on. So you're always fully utilizing. All right. So in summary, I'll show you how you can use Numba to scale up your single node code, help you fully use your machine, and that you can see how Ufang is just easily changing one string. You're going from CPU to GPU. Dask, so the thing is Dask, you can easily scale up from a laptop. I'm actually scheduling the example from a laptop to the cluster. Actually, in this example, it's one machine that I was running the live demo. But you've seen how that works. And then when you combine, you can easily get, even on a single node, this helps you, Dask helps you use Numba in multi-GPU fashion, in multi-node, easily go to GPU clusters. And you can, both of this Numba and Dask are free, open source. You can get Anaconda, download, Conda install Numba Dask. And there are more features, there are more details to all these 2 packages I haven't shown. So please visit the website for these projects. And once you, this progress announced before, we are also very honored to receive a grant from the Morg Foundation to help us move Numba and Dask to version 1.0. And we want to thank the Foundation for this generous offer. And please look at our developer blog for more details of these grants. And thank you, and open for questions.
We have lots of time for questions.
Hi, thanks. I was curious how the performance of using Numba plus Dask compares to using other like computation graph libraries like TensorFlow or Theano.
I haven't compared to TensorFlow yet. I have tried Spark. Mm-hmm. I did a presentation at Spark Summit. And for the GPU case, it's very hard to kind of ban Spark to use GPU or consider the GPU. And I end up doing a really weird hack. I have to use Dask within Spark. Don't do that, don't try that at home. It's weird. And but that's kind of what's Yahoo, what's this called? They have similar, they did something like that. Something I forgot what it's called. Cafe on Spark. Yahoo did that. They have their MPI-like cluster spawning within a Spark cluster. But,
thanks.
Yeah.
Combining Quadro and GTX cards, how does the compiler handle the precision? Is it force you to use single precision, or does it do tricks to get double precision out of a single precision card?
We don't do any tricks like that. Either using single or double precision is part of your code. Your arrays, if it's coming in float 64 arrays, you're doing operation on float 64, it has to be double precision. We don't do any tricks to mimic double precision on single precision. And double precision is supported in the hardware, although the throughput is very low on like older generations.
So you showed that for the distributed system in the code, all you had to do to make it distributed was add a couple of lines. Mm-hmm. And to set up the other computers, is it just conda install dask on those computers, or is it more involved than that?
Yeah, conda install dask and launch the schedule with that one command, launch workers on each node with the other, the dask worker. and point it to the scheduler. So it's really simple.
Do you have the scheduler somehow aware of the memory constraints of each of these GPUs? Or are you just making sure that the job is sort of small enough that it won't like a K40 is twice the on card memory as like a K20? Just making sure that it fits in, or is this something we can add into the scheduler?
Currently, Dask is not GPU aware, and so the programmer has to know that it kind of fits. Otherwise, you get a crash. I should say raise exception, not crash.
Have you tried doing this with something like EC2 or any virtualized hardware where you have access to an NVIDIA GPU with drivers and everything, or only bare metal machines?
I don't know if I haven't seen a case where virtualized, like a VM can access the CUDA. We don't have that set up, so it's always bare metal machine. Are you talking about like on Amazon? If that works, if you're thinking about the Amazon cloud service, that works, but maybe not as good performance. I haven't tried myself. Yeah.
So I saw that you have an interface to get the individual grid IDs, and I know that you can often get multiples of performance if you do things like coalesce memory into a shared space. Is there any access to sort of the shared memory or other layers built into Numba?
Yes, you can. There's access to shared memory, local memory, and you can make constant memories as well. So yeah, you can do all that. And then all the synchronized primitives are available, but you have to look at numba.party.org for the full API. Yeah.
So we still have a couple minutes, but I'd like the next speaker to come close to the podium and set himself up, or herself, I can't remember. And we still have time for a couple questions.
Yeah, quick question. Do you support OpenCL and AMD?
Oh, AMD is something that we are working in progress, but that we are not using OpenCL or now SPIR-V. We have actually a stale branch for OpenCL support, and but the OpenCL is not ready yet. Our use case requires more features. But yes, AMD support is coming.
Hey, so I assume you also have worried about things like data localization, so you don't end up over here. Sorry, you don't end up accidentally, transferring the same array to the GPU twice.
Oh,
is that something Dask does, or do you have to do that explicitly? Or
Dask handles that, and it has it's caching, and it knows the locality. It tries not to move things that are too big around.
Okay. All right. Thanks.
One last question, or let's thank the speaker again.